Every time two galaxies collide, it looks like gravity has a clean goal: pull, merge, and settle. But astronomers keep seeing mergers stall, as if the universe reaches an invisible ceiling. The galaxies get closer, brighten, and stir up tidal tails. Then the process slows dramatically, even when there's plenty of time left in the age of the universe. So why don't they just finish the job? And here's the twist. This stalling seems to depend on distance, on cosmic expansion, and on something we can't see: dark energy. In other words, there may be a merger horizon, a boundary beyond which the universe itself makes coalescence harder. It's a misconception to think gravity always wins simply because it's attractive. Beyond some scale, gravity competes with the behavior of space. And to understand why mergers stall past light speed, we have to understand a strange fact about cosmic motion. Light speed isn't just a speed limit for travel through space. At large distances, it becomes a measuring stick for whether regions of space remain in causal contact at all. To set the stage, imagine the typical path of a galaxy pair. Two galaxies approach, their outer stars and gas feel each other first, and the system forms a tidal handshake: arms, bridges, and stripped material. Meanwhile, their dark matter halos overlap, creating a complex gravitational environment. If the galaxies are close enough, friction-like effects in the dark matter, often described through dynamical friction, slow the relative motion. That friction comes from the gravitational wake one halo induces in another, like a boat dragging a disturbance through water. Over billions of years, the orbit decays and the galaxies merge into one. Before the modern precision era, this picture seems straightforward. If halos overlap and friction acts, mergers should complete. But observations, especially of galaxy clusters and large-scale structure, showed something else. Even in environments where we expect interactions to continue, many pairs linger without merging as efficiently as naive estimates predict. The before state is the mismatch. We can model gravity and friction, yet the rate of completed mergers drops with increasing separation and with cosmic epoch. That's when dark energy enters the story, not as a new force tugging on galaxies, but as the geometry and expansion history that reshapes the tug of war. Here's the core mechanism, and the deep dive begins with what light speed really means in an expanding universe. In an ordinary Newtonian setting, an object's influence spreads instantaneously only in the math. In reality, information and causal effects spread at or below the speed of light. In a universe with expansion, distant regions can recede so quickly that even if gravity is attractive, the galaxies cannot coordinate their long-term interaction. Think of it like two dancers trying to reach each other across a ballroom while the floor itself stretches like elastic. If the elastic stretches too fast between them, their steps can't close the gap, not because the dancers stop moving, but because the space between them keeps expanding faster than signals can bridge the distance. Dark energy in the simplest model behaves like a smooth component that drives accelerated expansion, that changes the effective horizon, the maximum scale over which events can influence each other in the future. Now, picture a merging pair inside a dark matter halo environment. Dynamical friction can work only if the system can continually exchange momentum through gravitational interactions. That requires an extended gravitational conversation between the halos, wake formation, perturbations, and the ability for those perturbations to remain relevant over orbital timescales. As the separation grows, cosmic expansion becomes comparable to the galaxy's mutual gravity in setting their relative trajectories. Past a certain scale, the expansion effectively outruns the pair's ability to tighten their orbit. Even if they are still approaching at first, acceleration can turn the approach into a stalling, or even a slow retreat in moving coordinates. The galaxies may remain within each other's broad gravitational domain, yet the detailed orbital energy that would allow complete coalescence cannot dissipate efficiently. The wakes blur into the background of expansion, like trying to create a lasting eddy in a river that is now flowing into a widening ocean. The discovery story is not a single telescope night, but an accumulating chain of evidence. Simulations that include dark energy reproduce a trend. Merger times grow sharply with initial separation, and beyond a scale, many pairs never merge within a Hubble time. Observationally, astronomers trace galaxy pairs across redshift and infer that the merger rate drops more than simple halo-based expectations. When researchers compare models, dark energy provides the missing leverage. It alters the timing and the causal reach of gravitational interactions. The idea of a merger horizon emerges from the same physics that defines the cosmic event horizon, the boundaries set by the future expansion history. It's not that galaxies stop obeying gravity, it's that the expanding space-time changes what obeying gravity means for long-range, time-dependent orbital decay. You can almost think of dark energy as adding a kind of background drift to the phase space of possible encounters. It doesn't erase attractions, but it limits how long those attractions can act coherently. The broader implications are profound. Galaxy mergers are not just fireworks. They are engines of cosmic evolution. Major mergers can trigger starbursts, redistribute gas, build bulges, and feed central black holes. If mergers stall beyond a horizon, the growth of massive galaxies slows and the morphological mix of the universe changes. That affects how we interpret the mass distribution we see today and how we link early conditions to present-day structure. It also feeds directly into cosmology as a test of dark energy. If dark energy controls a merger horizon, then the statistics of galaxy interactions become an indirect probe of the expansion history. In practical terms, surveys mapping close pairs and identifying merger remnants can constrain how strongly expansion suppresses long timescale coalescence. That means the invisible component driving acceleration might be revealed not only by supernovae or the cosmic microwave background, but by the survival rate of near collisions in the cosmic ledger. And there's a conceptual payoff. Light speed is often treated as a hard limit for objects moving through space, but on cosmic scales, the more relevant limit is causal contact, whether gravitational influence can remain effectively coupled across the expanding geometry. The universe can expand in ways that make two regions forever unable to turn their mutual attraction into a completed merger. That's a subtle but powerful lesson. Gravity is not a guarantee of outcomes. It's a competition with the structure of space-time itself. Dark energy, by changing that structure, defines which gravitational tails can finish their plot. So where does this leave us? We started with the surprise, galaxy mergers that should complete seem to stall. We place that in context, when friction and gravity alone can't reproduce the observed slowdown. Then we dug into the mechanism. An expanding universe reshapes the timeline and the causal reach of gravitational interaction, and dark energy makes a boundary where the long-term orbital tightening fails. In that picture, beyond light speed doesn't mean galaxies locally violate physics. It means the separation becomes so large that the pair can't exchange the information and momentum needed to dissipate into a merger within cosmic time. The horizon is not a wall. It's a consequence of the universe's future. If dark energy can decide which encounters become unions, then the architecture of the cosmos writes the ending before the galaxies even meet. If you want more explanations like this, subscribe and let's keep chasing the hidden rules of the universe.